Good afternoon, boys and girls. So today I'm going through the grade 11 geography paper 1. I'm covering the first, that is the atmosphere. First question, that is the atmosphere. That is the question that I'm going to go through. Let's go through the paper so that we do not waste time. Let's go through the paper so that we do not waste time. So here's our paper. It reads climate and weather and geomorphology. So we are going through the first part of our paper. It reads, the fig shows global air circulation. Match the descriptions below with the term or concept from the diagram. You may use a term or concept more than once. Write only the term concept next to the numbers, question numbers 1.1.1 to 1.1.7 in the answer book. For example, 1.1.8, the polar belt. So this is our global air circulation. I think you understand the first thing that I can actually talk about is you need to be well versed with the pressure belt. That is your equatorial low, which is a low pressure. Then you've got your subtropical high, which is both north and south of the equator. Then you've got the subpolar low, which is also both north and south of the equator. Okay. Then we also have the polar high. So this is your diagram that shows the pressure belts. That's what it's showing. It is also showing also the planetary winds. We have got your easterlies, that is between, and in this latitude, that's where you've got your tropical easterlies, north and south of the equator. You also have your westerlies. You can see also the wind belt where the westerlies is located. That is both north and south of the equator. We also have here the polar easterlies. We have the polar easterlies between our polar high and our subpolar low. That's where we have got the polar easterlies. The polar winds is also known as the polar easterlies. That's where we have it, okay? So tropical easterlies on both sides. We have got the westerlies, tropical westerlies. Then we've got the polar easterlies. That is between your subpolar low and your polar high. We've got your polar easterlies or polar winds, but we call it them the polar easterlies. So you can also see them in terms of how they move. Remember, our wind, it moves from high to low pressure. That's why you can see with these arrows, it's moving from high pressure, which is our subtropical high, towards the equatorial low, which is low pressure. That is where it is converging at the equatorial low, or we call it also the intertropical convergence zone. It is also known as the doldrum. These tropical easterlies, they are also known as trade winds. They are also known as trade winds. When it comes now to your westerlies, they are also known as prevailing winds. So let's go through the question so that we don't waste time. The feral, okay. The feral cell is associated with the belt where we find our feral cell is here. Of course, feral cell is associated with these winds, which means we find it within the westerlies. That will be the westerlies. That is your answer. We find it in this belt. That is where you have got your feral here, you have got your polar cell here, then you have got your Hadley cell here. I'm not going to do those arrows how it moves, but I'm just indicating this is where you've got your Hadley, this is where you've got your feral cell, this is where you've got your polar cell. So that's what this is all about. This is where you've got your Hadley, both north and south of the equator. This is where you've got your feral, both north and south of the equator. This is where you've got your polar, both north and south of the equator. So the feral cell is associated with these winds. It is associated with the westerlies. It is associated with the what? The westerlies. That's what it is associated with. It is associated with the westerlies. I've shown you this is where we have got our feral cell. Then ITCZ is associated with this belt of pressure. The ITCZ is your intertropical convergence zone, which is the zone of low pressure. So this is your ITCZ. Another name for equatorial low pressure belt is the what? Intertropical convergence zone. So that is the answer then. Then very cold winds, obviously we are talking about the polar winds. or we can call them the polar easterlies. The polar winds, they are very cold because of where they are found. You can see the further you are from the equator, the colder it is. So we have got the polar winds or the polar easterlies here. Okay, that is 1.1.3. Then we have got the Hadley cell is associated with these winds. Which winds are associated with the Hadley cell? That's where you've got your easterlies. This is where you've got your Hadley cell, both. So which means we are talking about the easterlies, the tropical easterlies, to be clear. The tropical easterlies, okay? Then very low temperatures in this pressure belt results in snow, 1.1.5. So we are talking about the the polar, very low temperatures in this pressure result in snow. So which means we are talking about the polar high pressure belt. The polar high pressure belt here, the polar high pressure belt, that's what we are talking about. The polar high pressure belt, that's what we are talking about, the polar high pressure belt. Then this pressure belt is located between 25 to 35. Okay, 25 to 35, you can see this is your subtropical high pressure. Subtropical high pressure, subtropical high pressure. That is your answer there. Then winds converge at this pressure belt, resulting in thunderstorms. So converging, which means this is what is happening. The winds are converging at the equatorial low pressure belt. They are converging. This is what this arrows show, showing the convergence, which means they are moving towards each other from the high towards the low pressure. They are converging at the equatorial low pressure belt, or ITC said. So that is your answer there. That is your answer there. So we have said in short, the Ferrel cell, this is where you have got your Hadley cell, your Ferrel cell, and your polar cell. Okay. ITC is associated with this pressure belt. ITCZ is also known as the equatorial low pressure belt. Okay, it's the same thing. Very cold winds, we are talking about your polar winds there according to the diagram. Hadley cell is associated with these winds. That will be your easterlies, because your Hadley cell is here. That will be your easterlies. Very low temperatures in this pressure belt result in snow. We are talking about, that is 1.1.5. We are talking about the polar high pressure belt. Polar high pressure belt. Then you've got the wind converge at this pressure belt, resulting thunderstorms. That is your equatorial low belt. Remember, think about the type of rainfall that you are likely to have. That's a convectional type of rainfall. So warm air rises. As it rises, condensation, there's unstable weather conditions, which is associated with the heavy rainfall, cumulonimbus clouds. Then we also have thunderstorms. Okay, that is what it is. Let's move on to the next one. The second question reads, refer to the fig, okay? Refer to fig that shows the relationship between pressure gradient and the Coriolis force. Choose the correct word, letters from those given in the brackets, which will make each statement geographically correct. Write only the letters next to the question number. So this is how we are going to answer 1.2.1 to 1.2.8 in the answer book. So this diagram, it shows you, okay? This is your high pressure, you can see here. This is your high pressure, you can see there's high pressure at the center, 1020. This is hectopascals or millibars. Here you can see it's 1012, which means there's low pressure. So there's higher pressure and the pressure decreases as you move outwards. This is why we say it's higher pressure. There's low pressure here, there's low pressure at the center, and it increases as you go outwards. So this is what makes up your high pressure, because there's higher pressure at the center and the pressure decreases going outwards. The isobar that we have here is 120 hectopascals, then we've got 116, which means there's an isobaric interval of 4 hectopascals. Same applies with B. This is a low pressure. Why? Because you've got low pressure at the center and the pressure increases as you go outwards. So the isobar here is showing 1012, then here is showing 1016, which means the isobaric interval, the difference in pressure between two isobars is what? 4 hectopascals or 4 millibars. That's what we have here. Okay, let's move on to the next one. Okay, it reads, wind blow from, usually our wind, it blows from high to low pressure. So since we have already seen where the high pressure is and where the low pressure is, so it becomes easier now. Our wind blows from high to low pressure. This is where we've got our high pressure. This is where we've got our low pressure. So it means it blows from A to B. That's what it means. It blows from A to B. That is the correct answer there. Coriolis pressure gradient force determines the speed at which air moves. So for speed, wind speed affects, the pressure gradient affects the wind speed. Okay, when you talk about the Coriolis force, okay, Coriolis force, this is the deflection of wind. Okay, as it is moving, like you see here, this wind was supposed to move from A to B, but because of Coriolis force, it has been deflected. That's the Coriolis force, which means in the northern hemisphere it's deflected to the right, in the southern hemisphere it is deflected to the left. Okay, so this wind, it was supposed to move from A to B in a straight line, but because of the Coriolis effect, okay, which is caused by the Earth's rotation, so what happens is it's deflected to this side. So you can see when you are standing here, which means this side will be your right side, which means we suggest that this is more or less like the northern hemisphere, because it is deflected to the right. It is deflected to the right when it moves from here to going that side. It's supposed to go there, but it is deflected to this side, which is the right, which suggests that it is the northern hemisphere. Okay, so this is what Coriolis force is. So the Coriolis force, what it does, it influences the wind direction. Okay, where's the pressure gradient influence the what? The wind speed. So we are saying that the pressure gradient, we are talking more about the wind speed. Okay, then when you talk about the Coriolis, we are more concerned about the wind direction, how it is deflected, how it is deflected. So the relationship now, Coriolis force influence the wind direction. You can see that it was supposed to move in this direction, but however, it was deflected to this direction. So the pressure gradient is supposed to move from there up to there. So which means when you talk about the pressure gradient, we are talking about in terms of the closeness of the isobars. If they are very close to each other, there's steeper pressure gradient. If they are further apart, which means they have gentle pressure gradient. Steep pressure gradient, it actually shows strong winds, and gentle pressure gradient shows what? Weak winds. That's basically what this is all about. So the answer here is force determine the speed at which air moves. So your answer for 1.2.2 is what? Is the pressure gradient. Is the pressure gradient. Then 1.2.3, Coriolis force or pressure gradient forces causes winds to deflect, change direction. Like I was saying now, this is your Coriolis force. This is your Coriolis force. I think I've already explained it. Winds are deflected to the right in the northern hemisphere, and they're deflected to the left in the southern hemisphere. That is your Coriolis force. Okay, in the northern hemisphere, winds deflect to northern hemisphere. Remember, I said northern hemisphere is deflected to the right. Then southern hemisphere, they are deflected to the left. Subsidence is associated with, remember, our subsidence is associated with high pressure, because with high pressure, we have got cold air. Cold air is very dense, so what it does is it sinks, it subsides. So there, the answer is subsidence associated with, that is high pressure. Then a geostrophic berg, winds blows when the pressure gradient and the Coriolis force is equal in strength. This is what we call the geostrophic flow. This is an upper air movement which flows parallel to the isobars when the pressure gradient and the Coriolis force are in equilibrium. So that is your geostrophic flow. It is upper air movement that flows parallel to the isobars when the pressure gradient and the Coriolis force are in equilibrium. Convergence is associated with convergence. Okay, we can go back here. Convergence, what convergence is associated with? Remember here, this is a low pressure. So air is converging. You can see this is a low pressure. What is happening? There's convergence at the ITC. So it means it's associated with the low pressure. Okay, convergence is associated with what? The low pressure. Okay. Then last one, 1.2.8, the pressure gradient is when isobars are far apart. So we are saying now, when the isobars are very close, okay, it's steep pressure gradient. When the isobars are further apart, it means it's what? It's gentle. That's what it means, which means here that is a strong wind. Strong winds, these ones are weak winds or light winds. Weak or light winds or light winds. Okay, so if the isobars are further apart, it's a gentle pressure gradient, which means light or weak winds. If the isobars are very close to each other, which are lines that shows areas of equal atmospheric pressure. So it shows that when they are very close, it shows that it's steeper pressure gradient, strong winds. Gentle, they are further apart, it means weak or light winds. That's what it means. Okay, let's move on to the next question. Refer to the synoptic weather map of Southern Africa. So what we have here, guys, just to make our life easier, this is what we have. I want you to take note of something. Can you see how this cold front is approaching towards Cape Town? How the cold front is approaching towards Cape Town, okay? Number one. Then the other thing that I want you to see is the date. The date that we have here, which is 23 June 2020. That's number two. Number 3, the next thing that I want you to see is the position of our high pressure system. This is our South Atlantic high, this is our South Indian high, South Atlantic high, South Indian high, which means they've moved further north. This is what they do, especially when it's in winter. They move further north, which means they shift their position in relation to the movement of our intertropical convergence zone. The intertropical convergence zone will be on top of the equator in the northern hemisphere. So you can also see here in the interior, inside, it shows you that they are clear skies. They are clear skies, which means there's calm and clear conditions in the interior, which are stable weather conditions. This is what is associated with winter, because we do not usually receive rains during the winter. It's only Cape Town that receives rain just because of the movement of our cold front, because of the mid-latitudes. So this already tells you that it is winter. Why? Because here what you have, the date is in July 23, July 2020, number 1. Number 2, you can check the approaching cold front. It shows you that this is winter. Remember, Cape Town receives rainfall when it's cold, which is in winter. So it's approaching towards Cape Town. That tells you that it is also winter. Number 3, our high pressure system, that is the South Atlantic high and the South Indian high, they change position in winter. They move further north. So this is also something to support that it is also winter. All right, let's go to our question now. The question now reads, I'll be referring to this one. It says, give evidence from the synoptic weather map that represents winter conditions. Remember, I told you the position of the high pressure system, number 1. I also talked about the date, which is in July. So we can talk about let me show you what shows that it is winter. Number 1, the cold front is approaching here in Cape Town, number 1. That's number 1. Number 2, the position of our high pressure system, the South Atlantic high over the Atlantic Ocean and the South Indian high over the Indian Ocean. Most of them, all of them, they move further north in winter. They move further north in winter, following the ITCZ that is now north of the equator. Then also you can see we have got clear and calm condition in the interior. So this is what shows you that it is winter. Okay, let's move on. Let's move on. The next one reads, determine the isobaric interval on the synoptic map. So we are looking at the difference in atmospheric pressure between two isobars. That is the isobaric interval. Okay, so if you check here, isobaric interval from 1012 to 1016, there's a difference of 4 hectopascals or millibars. If you can check also from 1016 to 1020, there's a difference of 4. 20 minus 16, there's a difference of 4 millibars or hectopascals. So the isobaric interval is 4 hectopascals. That is the correct answer then. So which means here determine is 4 hectopascals or millibars. That is the isobaric interval, which means the difference in atmospheric pressure between two isobars. Okay. Give the weather condition of the weather station at Port Elizabeth. Give them weather conditions of the weather station at Port Elizabeth. We are going now to our synoptic weather map. So the weather station that we are looking at now is, where is it? This is Port Elizabeth, okay? This is Port Elizabeth, okay? So we are giving the weather conditions. We are giving the weather conditions of this is shown here. So what do we have? We have got 19. You remember your weather station model. 19 is your air temperature, which is 19 degrees Celsius. Then you've got your dew point temperature here, which is 18 degrees Celsius. That is your dew point temperature. Then you can see that it's clear. Okay, cloud cover is clear. It shows you that it's clear. The wind direction, you can see from where it's coming from here going towards this direction. That's what makes it northeasterly. So you look, we name the wind direction according from where it's coming from. So it's heading towards this. This shows you where it's heading towards. This shows you where the wind is coming from. So it's northeasterly wind. Then what else? The wind speed, you can see the way it is. This is 5 knots. This is 5 knots. If it starts from here going like this, it's not at the end. So that is 5 knots. So this is your weather at Port Elizabeth. We have said 19 degrees, which is your air temperature. Dew point 13 degrees Celsius. Cloud cover is clear. Then wind direction is northeasterly. Then what else do you have? The wind speed is 5 knots. So that is your weather there at Port Elizabeth. That is the weather condition at station at the Port Elizabeth. Name the high pressure cell at A. The high pressure cell at A. What do we have at A now? Let's see. High pressure cell at A. So this is your South Indian high pressure. It's over the Indian Ocean, South Indian high pressure. So your South Indian high pressure is over the Indian Ocean. We call it the South Indian high pressure. Then this one is the South Atlantic high pressure. But the question is asking us about A, so which is the South Indian high pressure. Okay. Then what else? Then we have got, how will the position of A decrease the rainfall over the eastern part of South Africa? How is it going to decrease the rainfall? How is it going to decrease rainfall over the eastern part? Okay. How is it going to decrease rainfall? We are talking about the position of our South Indian high. How is it going to decrease the rainfall on the eastern part? This one, how is it going to decrease the rainfall? There will be little or no rainfall because the cell A is closer to the land. Remember, we said that it has moved north during winter. It moved further north because of the shifting of our intertropical convergence zone. So it is closer to the land. So that's why we have little or no rainfall. It has moved further north. Why? Because of the shifting of our ITCZ. So there's likely to be little or no rainfall if the pressure A cell is close to the land. Number two, less moisture is carried over the sea to Port Elizabeth. That's another thing. High pressure cell has reached over land causing descending air. It has reached over land causing descending air. Okay. High pressure has reached over land causing descending air. Okay. There is higher pressure. Of course, it has reached, which means it's elongated. You can see the isobars, the way it's elongated. So it is how it actually causes a descending air. Plus also there is another high pressure that is in the interior, that is Kalahari, which is too much subsidence. So that's basically what happens there. Let's move on to the next one. Then the next question reads, explain how the warm and cold ocean currents on the eastern, western part of South Africa could control the temperature of the South African winter. So basically what we are saying is over Cape Town, which is part of the Atlantic Ocean, we've got the South Atlantic high. Of course, there we have got the cold ocean currents. I'll give you an example, the Benguela current. Of course, that is coming from the Atlantic, over the Atlantic Ocean. Okay, here is a cold ocean. So we have got the cold Benguela current. Of course, here we have got the warm because it is close to the warm ocean, that is your Indian Ocean. So the question now is asking, I just wanted to show you, Atlantic Ocean, cold, then close to the Indian Ocean is warm and moist. Okay, let's answer the question now. So the question is saying, explain how the warm and cold ocean currents on the eastern and western side of South Africa would control the temperature of the Southern African in winter. Okay, South Africa in winter. So what we can talk about here, guys, is number one, the western side where we have got Atlantic Ocean, where we have got the South Atlantic high. The western side of the country would experience much lower temperatures because of the influence of the cold Benguela current. Okay, so we are saying now the western part where we have got the Atlantic Ocean is a cold ocean. So it's likely to experience much lower temperatures because it's a cold ocean, okay? Because of the cold Benguela current, okay? It's likely to experience very low temperatures because of cold Benguela current. The eastern side now is over a warm ocean. So what will happen? The eastern side of the country would experience moderate temperatures because of the influence of the warm Mozambican current in winter. So that is likely to happen from a warm ocean, from a cold ocean. Low temperatures here, warm ocean, we are likely to have moderate because of the warm Mozambican current here over the Atlantic Indian Ocean, where we have got our South Indian high. Okay, let's move on to the next question. The next question that would be number 1.4. Okay, start the fig based on the diagram showing warm, dry winds that blow over the North American and European continents. So obviously what comes to your mind now is the fohn winds. What comes to your mind is the fohn winds. Okay, is the fohn winds. That's what comes to your mind. So this is the diagram that we have. You can see on this, there's moisture-laden winds. Of course, there's clouds obviously on the windward side. There's clouds obviously on the windward side. But on the other side, which is the leeward side, of course, this is when the dry, warm air is descending, okay, on the other side, okay? Then warm, dry winds is on the other side. This is the windward side. This is the leeward side of the mountain. You can also see here it's the same thing in the Alps, of course, moisture-laden winds, but on the other side, we also have what? The warm, dry winds that are descending, okay? So what is happening is we have something like this. Okay? So we are saying now on this side, we have got warm air that is rising, warm and moist air that is rising. As it is rising, it cools, condenses, then clouds form. On this side, we have got rainfall. But the same parcel of air is still rising, then it goes on the other side. On the other side, since it has lost moisture on this side, which is more like this side where we have got rainfall, there is rainfall, condensation has taken place. So this side, it has lost most of its moisture. So when it's descending on this other side, which is more like your A, it's warmed up adiabatically, which means for every decrease of 100 meters in altitude, the temperature increased by 1 degree, which means it's going to be warm and dry. That's why in most cases it results in veiled fires. That's why in most cases we are defining it as a warm, dry air that descend on the leeward side of the mountain, because it is warm and dry. As it is descending, going downwards, it is warmed up adiabatically, which means for every decrease in altitude of 100 meters, the temperature increased by 1 degree. That's why here we have it as moisture laden. It rises. As it rising, it is adiabatically cooled, which means for every increase in height on the windward side, which is this one, the temperature is dropping by 1 degree. Here on the other side, leeward side, for every decrease in altitude, the temperature increased by 1 degree, altitude of 100 meters. So that's what is happening there. So windward side, there's adiabatic cooling. Then leeward side, there's adiabatic warming. That's why here we have got moisture laden, we have got rainfall here, clouds forming. Then on the other side, when it has lost most of its moisture, is it is descending, it is adiabatically warm. That's what makes it warm and dry. Okay, let's go through the question. Provide the local names of the warm, dry winds located in A and B. So in A, where we have got this area, we are saying now it is called what? North American side, it is called on this side, it is called what? It is called the Chinook. It is called the Chinook. That's what it is called. It is called what? The Chinook. C-H-I-N-O-O-K. Then on B, where we have got B here, it is called the Fohn winds. It is called the Fohn winds. So these are the different names that are given. Okay. Is the wet adiabatic lapse found at windward or leeward? It is found on the windward, which means where we have got moisture-laden air. The warm air by its nature is very light, so what it does is it rises. So this is the windward. Windward, the other side is the leeward. So it is found on the windward. That's what we call wet adiabatic lapse rate, which means we are saying now for every increase in altitude of 100 meters, the temperature dropped by 1 degree. That's what wet adiabatic lapse rate is all about. On the leeward side, where there is warm and dry, there's what we call dry adiabatic lapse rate, which means for every decrease in altitude of 100 meters, the temperature increased by 1 degree. So at wet adiabatic lapse rate, there is a decrease of temperature with an increase in height. With dry adiabatic lapse rate on the leeward side, there is an increase in temperature with a decrease in altitude. That's basically what this is all about. So we're done there. Why is the wind dry at A and B on the? Why is the wind dry at A and B on the maps? Okay, why is it dry on this side? Warm and dry winds, warm and dry winds. Why is it dry? That is your 1.4.3. It is dry because on the windward side of the mountain, condensation occurs and moisture is released in the form of precipitation. As the wind rises and moves over the mountain, more moisture is released and eventually becomes drier. On the leeward side, descending air causes the last available moisture to evaporate. As it descends, it heats up. Or with descending air on the leeward side, there is no condensation. So we are basically saying that when you look at this diagram, as it is rising, okay, moisture is released on the windward side, so that when it gets to the other side, the leeward side now, it is warmed up adiabatically, or whatever moisture is left is evaporated because there is adiabatic warming that is taking place. That's basically what we are talking about. So we are saying if you look at this side, which is the windward side, there is a decrease of temperature with an increase in height, which is most of the moisture is lost here where condensation takes place, clouds build up, then we have got rainfall. But on the other side now, all the moisture has been lost on the windward side. So when it comes to this side, it is now dry. So that's why we are saying now it is adiabatically warmed. That's what is happening. In a paragraph of approximately 8 lines, explain the influence that this warm, dry winds have on economic activities, on areas indicated on the map, economic activities. So we are saying now, where it is going to descend, where it's going to be warm and dry, is likely to result in wildfires. So what are some of the influence have on the economic activity in the area indicated in the mapped area? So we can talk about, we want to talk about them differently. So let's start with the Chinook. What will be the the influence or the economic activities? The warm air in this area, it warms up, okay? The warm air, what it does in this region, it warms up. The warm air melts the snow during winter because the temperatures are high. So the snow starts melting. So the warm air, it melts the snow during winter. This allows the agricultural activities to proceed as water is available, which means when snow melts, we are likely to have floods or avalanches. Then obviously this provides water for agriculture. That's number one, economic influence. Then it also causes more pleasant working conditions during the colder months, okay? Which means it also causes more pleasant working conditions during the colder months. Then melting snow may also cause floods. Okay, obviously when we have got more water, it actually makes it easier for agriculture to take place. That is on the part of this A in Chinook. Then on our phone now, where we have got the Alps, we are saying now the physical dehydration of people influence production negatively, which means it is associated with high temperatures. So there's going to be a dehydration because it is associated with the high temperatures. Then the other thing, droughts dry up agricultural land because obviously the temperatures are high evaporation rate, so that also affects agriculture. Wildfires, they also destroy agricultural land. Remember, we are talking about the economic activities. That's why we are including all this, because how people can actually generate an income, how it affects the profits and things like that. That's basically what we are talking about. So this takes us to the end of this question about the Chinook and the phone winds. Let's move on to the last part. The last part is about desertification. Refer to the extract of the effects of desertification in the Sahel region. The effects of desertification in Africa. Okay, desertification is a process that destroys fertile land. Okay, that's the first thing you have to take note of. What does it do? It destroys fertile land. This can be caused by drought, overpopulation, overfarming, deforestation, and climate change. So these are some of the human activities that actually results in desertification that you should take note of: the drought, overpopulation, overfarming, deforestation, climate change. The most vulnerable region is a 3,000 miles stretch of land that includes countries in the Sahel region of Africa. Sahel is an area between, you have to know where this Sahel region is, between Sahara Desert and Sudanian savanna. This region is under constant stress due to the frequent droughts and soil erosion. A dense forest can become filled of dust in a matter of years, making mass migrations inevitable. Africans frequently migrate south in search of fertile land. Okay, agriculture in Africa tends to result in low productivity as most of the land is characterized by semi-desert. Clearing of land trees also reduces the structure of the soil. Coupled with wind erosion, the topsoil blows away and leaves the desert-like land. The country that is arguably the most damaged by desertification is Senegal. Migration in Senegal are common as wind erosion, deforestation, and climate change wreaks havoc on farms and livestock. Those most affected by desertification in Senegal move to Gabon, a country to West Africa, even to Europe and South America. More than half of the Senegalese work in agriculture, and desertification forces those with meagre profits to move elsewhere to escape poverty. So these are some of the effects of poverty that are being highlighted here in this extract. So let's go through the questions so that we don't waste time. According to the extract, state one human cause of desertification. Remember what we talked about. We have got overpopulation, we've got overfarming, we have got deforestation. These are some of the human causes, which means overpopulation, overfarming, deforestation. That is your answer there. It's straight and to the point. You only write one. Name the region most vulnerable to desertification in Africa. Obviously, we are talking about the Sahel region. The Sahel is an area between Sahara Desert and Sudanian savanna. So it's the Sahel region. Okay. Then why is fertile soil important to the people of Africa? Why is fertile soil so important? 1.5.3. Why is it important? Of course, we rely more on agriculture. They are subsistence farmers. They depend on fertile soils as a source of food. Okay, they also farming is a source of income. So we are more into farming. We need fertile soils so that we can actually farm. Okay. What social impact would lack of fertile soils have on the people of Africa? If we do not have the fertile soils, what are the social impact? 1.5.4, there is reduced crop production, therefore less food food. We have got food insecurity. Obviously, people would die of starvation and malnutrition because we don't have fertile soils that we use to grow crops that also help us to have food. Okay, it will lead to rural urban migration because those people that are relying on farms on the rural area will migrate to the urban area. So that will be the social impact there. How does desertification in Senegal have negative impact on other countries? So we are saying the desertification that is taking place in Senegal, how does it have negative impact on other countries in Africa? Obviously, people are bound to migrate at some point. People from Senegal migrate to other countries to use their resources, making a living. Okay, so people now, they are moving to other countries, which means there's going to be pressure on resources on those countries that they are migrating to. This puts a strain on the land and less food is produced. Local citizens are unable to feed themselves and depend on the government on foreign donations. That is what happening. They are not able to feed themselves because they end up depending on the government and foreign donations. There can be also conflict between locals and immigrants comes as great economic cost. Okay, the locals and immigrants move to urban areas, which puts pressure, strain on the host country's economy. Okay, these are some of the challenges that we have. Okay, the last part. Suggest 2 management strategies that could be implemented to reduce or combat the spread of desertification. What can we do to reduce the spread of desertification? What can we do? The first thing that we can do is we can actually plant trees. We can actually encourage afforestation programs where we plant trees. We can also implement effective soil management that will include organic fertilizers, crop rotation, and contour plowing. These actually help to retain the natural soil fertility. So anyway, also trying to reduce the spread of desertification. We can also allow the land to be fallowed for a period of time to renew itself, which means we are not going to till the land all the time. We allow it just to stay the way it is naturally without being tilled. That's what we call by fallowing. We allowing the land to be fallowed for a period of time to renew itself naturally. Then we can support local farms with education and training of sustainable ways of farming. Okay, we can also have programs for rainfall reliability and planting drought-resistant crops. There are some of the crops that can actually do well. There are drought-resistant crops. They do not require a lot of water, so we can plant that. So in that way, we can also help. Then natural action plans that could oversee land ownership and encourage subsistence management of land. These are some of the things that we can actually do in order to make sure that we combat the spread of desertification. So boys and girls, I have gone through the Eastern Cape. I've gone through the Eastern Cape grade 11, November 2022 Geography paper 1. So I have done the first part, which is atmosphere and weather, where I looked at the global air circulation, and that is part of your 1.1. I also looked at the pressure gradient and the Coriolis force, which is the main concept in your 1.2. Synoptic weather map, the main concept in as far as your 1.3 is concerned. Analysis of the synoptic weather map, that is 1.3 is concerned. Then 1.4, it was an emphasis on phone winds. That's what we covered on 1.3. 1.4, that was the question was all about. Then 1.5, it was about desertification. So please go through this question, go through this video, comment and tell me if you have got any challenges so that we can know how to help each other. I've gone through this. Then I'll also upload paper, the second question 2, which deals about geomorphology, which covers geomorphology. I'll do that, but at the moment, let's enjoy atmosphere and weather, which is part of our geography, term 1 in grade 11. Please don't forget to subscribe to my YouTube channel. You can just click the link on my bio. Subscribe to my channel, please. Subscribe to my channel, please. You just subscribe. It's just clicking. Just click the button to subscription. Then I'll be happy. Thank you so much and have a blessed day.